Okay, so for today we're going to talk about the chi-square test of independence, and we're going to use this example. It says a study was conducted to investigate if the preference of food in a canteen is independent of grade level, and we are given the following table of results for the preferences of students. Hmm. We do know that we are going to do the chi-square test of independence here because of the keyword independent. So for the chi-square test of independence, we usually are required to state the null and alternative hypothesis. Okay, so that's our question A. The null hypothesis is denoted as HO, and the alternative hypothesis is denoted as H1. The null hypothesis is usually specifying that our two variables are independent of each other, and the alternative hypothesis is going to be not independent. So we simply identify what are our two variables, and we say for our null hypothesis they are independent. Okay, so we're going to say food preference is independent of grade level. Okay, and for the alternative hypothesis, we're going to say food preference is not independent of grade level. For the second question, we want at a 5% level of significance, we want to test whether the choice of food in this canteen is independent of grade level by first using the critical value, which is given to be 16.919, and the second is computing for the p-value. So this is now when we actually do the chi-square test, and we have to input our contingency table into our matrix. So the contingency table will have a maximum of 4 rows and 4 columns in exams. So that's the maximum that I have here. So we go to second matrix and we click edit matrix, and then we input the number of rows and the number of columns. So number of rows first, 4 rows, 4 columns, and then we input the values from our contingency table as you see it appear in the question. So now I'm inputting horizontally, rows first. Okay, when you finish inputting, make sure you double check that your numbers are correct. So I'm going to double check vertically. Okay, so when you're satisfied that you have inputted the correct values into your matrix, you are now ready to do the chi-square test of independence. So we press statistics, we go to the right for tests, and then we press the top button because the chi-square test is closer at the bottom. So that's option C, chi-square test. So we say enter. The observed values, we inputted that in our matrix earlier, and we used matrix A. If you used another matrix, that's totally fine. You can just change this name by just pressing second matrix, and then you can choose whatever matrix you have put in there. Okay, so let's just leave that at default to be A. The calculator will be inputting the expected values into matrix B, so let's leave it at that, and we press calculate. Okay, so it gives us a chi-square calculated value and a p-value. So the first option that we want over here is test using the critical value. So for the first part, our critical value is 31.7. So our conclusion will be based on whether this critical value is greater than whether this calculated value is greater than the critical value. So we say 31.7 is greater than the critical value of 16.919, and if that happens, our conclusion is going to be reject the null hypothesis. The requirement is we reject the null hypothesis if the calculated value is greater than the critical value, and you have to explicitly write that in your answer for comparison. You should not just generally say chi-square calc greater than chi-square critical. Okay, so it's best that you write the specific values that's relative to the problem. Okay, so that's one option of deciding whether to reject or accept your null hypothesis. The second option is using the p-value, which we have for question II over here. So the chi-square test also outputs a p-value, and you see that that p-value is 2.24 times 10 to the minus 4. Don't forget this notation. It means times 10 to the minus 4, and this is actually a very small value. It's 0.00024, okay, and that is going to be less than our level of significance, which is 0.05. So we compare the p-value computed by the calculator to the significance level in decimal form, and if this p-value is less than the level of significance, we're going to reject HO. These two conclusions should actually agree with each other. In exams, you will just be tested on one or the other. So if the critical value is given, perhaps it is expected that you are to compare the chi-square calculated value with that. But if it is not given, that should be okay. You can still compare the computed p-value with the level of significance, which will always be given in your question. The next here is to show that the degree of freedom is 9. So if you notice, that degree of freedom is also given by your chi-square calc test, and this degree of freedom is 9, but you are sometimes required to show why that became 9. Okay, so the formula that you use for the degree of freedom is number of rows minus 1 multiplied by number of columns minus 1. So I have 4 rows. I subtract that by 1, and I also have 4 columns. I also subtract that by 1. Okay, so I say that's 3 times 3, and that gives you a value of 9. And the last question that they could probably ask would be, show that the expected value of grade 12 students choosing hot food is 43. Okay, so hot food and grade 12. Okay, so the expected value is actually given in your matrix after we execute the chi-square test. It's given here in your matrix B. So earlier there was an expected matrix table, and this is your matrix. Okay, so the number corresponding to 50 here is 42.984, which is 43.0, which is specified here. Okay, so we need to show working though how it became 43.0. Okay, so what we need is the total for the row for grade 12, multiply that by the total for the row for hot food, and then divide that by the total for all the columns or all the rows. Okay, for us to be able to do that, we could add these manually. So for example, I have 50 plus 35 plus 60 plus 22. I add that, that's 167. And I add also this column, 35 plus 28 plus 35 plus 50. So that will have a total of 148, but I also need the total down here. So if you want, you can go ahead and keep adding everything else so that you can come up with a total. But I would add this using matrix notation and sigma notation just to make it faster, because these values are already in the matrix. So if you take a look at the matrix A, okay, so this can actually be accessed from your second function matrix A, and you can say 1 comma 1 is actually the number that corresponds to the first row in the matrix and the first column in the matrix, which is 35. So each one has a special name, and I could just go ahead and add all of those in one row, for example. So I go to sum of all these matrices. So I'm going to add, for example, all the matrices, all the elements in the matrix from row 1 and all the columns ranging from 1 to 4. Okay, so this is me adding up elements in A 1 1 1 2 1 3 1 4. This is 1 1 1 2 1 3 1 4, and that is 131 as our sum. Okay, so if I go and change this to the second row, so I'm adding up all the elements in the matrix from 2 1 2 2 2 3 2 4. That's going to be 124, and then I do that for the third row, and that's going to be 153. I will just have to confirm that with the fourth row, if that is indeed 167, and yes, that is 167 over here. Okay, so that I did not have to manually input them again. Okay, so if you are willing to understand this notation, you can go ahead and use that because it's faster. Otherwise, you can just keep adding manually. Okay, so now I have all these sums. I'm just going to add them all up. 153, 124 plus 131. So I'm adding all these values because I need that in getting the expected value later. Okay, so this is the total. Okay, so the expected value for the grade 12 students choosing hot food is going to be row total times column total divided by the final total over here. So that's going to be 167 multiplied by 148 divided by 575. So 148 times 167 divided by 575, and that's going to give me 43.0 to the specified accuracy over here.